So this event is, of course, about a combination of things. It's science, it's engineering, it's invention, it's personality. And I'd like to say just a little bit about all of those with respect to John. Let me start by saying that all of us have had, at some point, the same experience of meeting someone for the first time and feeling immediately a sense of warmth, respect, recognizing that you're dealing with someone who's significantly smarter than you are. And I had that yesterday with John's son. So I was fortunate enough to spend the first 20 years of my life here at MIT, and then I moved to Harvard. And at MIT, when you come up with something new, you stop your colleagues in the hall and you say something about it, and they say, "That's really neat. What's it good for?" That's called engineering. Terrific. You do the same kind of thing at Harvard. You come up with something new and you stop your colleagues and you say you've done something, and they say, "That's really neat. Why is it interesting?" That's science. Except, by the way, we don't use the word neat at Harvard. So John learned science the other way around. He worked with a very, very fine physical chemist here, Keith Nelson, who taught him what science was. And then he came to Harvard, where he learned something about material science, and that's what a material is. It's a concrete block or a piece of plexiglass, and the question is, how does the stuff that make it up make it what it is? He then went to Bell Labs in the years when Bell Labs was first strong and then beginning to drift down a bit, where he made a very important set of discoveries which taught him how you connect the world of electrons and computation with the world of materials and science. So he had all the pieces. From there to the University of Illinois, where he's done two things that are really quite remarkable. The first is that he has connected a world which has been built on the idea of hard, rigid stuff, silicon, with the world of stuff that's really flexible and soft. One of his major articles of materials with which he works is the same thing that you use to caulk the cracks in your bathtub. And he's managed to do a lot with that. And that's good stuff, because it puts together an idea of hard and an idea of soft in a way that people hadn't thought about at all. And it's a form of invention. But the more serious work is the work that he's being recognized for here, I think, which is a much more radical notion, which is putting together the idea of electronics, information, disembodied from us, and life, that is, the brain, the heart, people. It's the kind of thing that you just really wouldn't think about. Now, there's a metaphor from archery that people use in describing some of these things. And the idea is that if you have a bow and an arrow, and you put them together, and you draw the bow, if you have the arrow, the sharp point, away, that means you're competent. That's a start. And then if you do this and let go, and you hit the target that nobody else can hit, you're skilled. But if you can hit the target that no one else can see, you're a genius. John Rogers.
there's nothing more rewarding or exciting or, quite frankly, more societally important than inventing. And the key thing is persistence and being able to stick with your ideas and continue to pursue them relentlessly.
At John Rogers Lab at the University of Illinois, his team is pursuing lots of ideas simultaneously. In fact, it's hard to know where to look first. From medicine to photovoltaics to microscopic printing techniques to LEDs, Rogers is reshaping ordinary materials to help address some of society's most pressing needs.
If you look at biology, it's inherently made of materials that are soft and curvilinear. And if you compare that to conventional electronics, you have a huge mismatch. And so we've been addressing that problem over the years, is how do we take a form of electronics like this and make it truly tissue-like?
Rogers' solution? Developing techniques to slice silicon into ultra-thin, flexible sheets.
So if you take these nanoscale membranes of silicon, you can put them on a sheet of plastic and make a bendable piece of electronics in that way. Two specific examples involve applications in cardiology and neurology.
In cardiac surgeries, his monitoring devices actually bond to the heart surface.
Almost like a piece of saran wrap. This device provides a window into regions of the heart that might be operating in an aberrant way.
In neurology, this same technology helps surgeons treating patients with epilepsy.
Instead of mapping electrical activity on the surface of the heart, we're mapping it directly on the surface of the brain. The electronics conformally wrap and drop into these deep fissures and folds that allows very precise, high-resolution measurements of the electrical activity of the brain. How much smaller we could make the cells.
Tackling another of society's most vexing issues, energy. Rogers turned his attention to the kinds of wafers used in photovoltaic arrays that turn sunlight into electrical energy.
What would happen if you took that wafer and in a controlled engineering manufacturable way exploded it into a billion tiny shards, spread them out in a low aerial coverage on a plate of glass, and then mount tiny ball-bearing lens optics on top of each one that have the effect of focusing very tightly incident sunlight onto those very tiny solar cells. And when you wire them all up together, you can generate tremendous amounts of power that way in a very cost-effective manner.
But wiring them together required special manufacturing tools. So Rogers and his team developed a printing technology to essentially write with silicon.
So we use very fine capillary nozzles, and by moving the stage around and controlling the voltages that we're applying to that nozzle, we can directly write those interconnect lines that tie these cells together in an electrical sense.
Another project of the Rogers Lab is developing low-cost digital cameras that mimic the human eye.
We configure arrays of silicon photodetectors on a hemispherical surface with about the same size and radius of curvature as the human eye. And if you do that, it turns out you can achieve a very wide-angle field of view, very low aberrations, very uniform illumination, even with the very simple, low-cost, lightweight imaging optics.
In his myriad scientific pursuits, John Rogers maintains his curiosity and excitement about the inventive process.
The laws of nature aren't simply a set of parameters that constrain the behavior of the natural world, but it's a set of tools that allow you to predict the future and engineer the world for favorable outcomes.
So I give you John Rogers. Congratulations.
Thank you very much. Well, thank you very much, George, for those kind words, and more generally for serving as a mentor and advisor over the years, really providing a role model for how to do research and innovation and commercialization. And I should say, what's obvious is it's an overwhelming honor to be here. It's just tremendous type of recognition for the kind of work that we've done over the years. receive a prize of this stature. And so I'd like to really extend my sincere thanks to Dorothy Lemelson, the Lemelson family, for establishing the foundation, making this award possible. Also, thank you to Michael Sema for sort of shepherding the process. I know the selection is difficult every year, and it's in fact profoundly humbling to think about the previous winners and my work kind of in that context. So it's really fantastic. I should thank also Ed Canton, who's been working closely with me over the last few months in the run-up to this event, putting together the video and so on. And I have to say, it's really configured to induce maximum embarrassment in the awards recipient. And so I'd like to congratulate you on engineering it in that way. It's really, really amazing. And so I'd like to also congratulate all the other winners. The event has been just a delight to participate in this week, and to get to know the other winners of the various awards, the Sustainability Award, the Student Awards. These are just remarkable people and incredibly impressive accomplishments. And maybe even more importantly, the Invent teams. It's just been amazing to see the youth and the energy and the bright faces and the creative spirit and the level of innovation that's going on in this next generation. And I think that kind of activity is really an imperative for this nation. It's not an option. And coming away from this event, it's hard not to be optimistic about the future, seeing these kids emerge into the next generation. And I think the whole thing is really a testament to the vision of the Lemelson family and the Lemelson Foundation, sort of enabling these kind of events and stimulating the next generation of innovators. And so, it's really a tribute to Jerry Lemelson himself. And so it's worth thinking about his accomplishments too. I think it's clear he's a unique individual, absolute one of a kind, more accomplished than any inventor since Thomas Edison. And what really struck me in kind of looking at his history is the sheer time span over which he was a productive inventor. It's just really remarkable, almost 5 decades. Hundreds of patents, and just breathtaking range of topical diversity as well. And I just pulled down a couple of drawings here from representative filings in this design for a tape cartridge and reader back in the early 60s, all the way to a patent on 3D displays that was issued in 1998. After his passing. And it's just remarkable, the range of stuff. And another sort of amusing point of information, if you look at the inventor list here, Dorothy Lemelson is included as a co-inventor. So congratulations on this very nice patent here. So the Lemelson Foundation kind of tasked me in this talk with kind of providing an overview of my own path and conclude with some perspectives and maybe some advice for the next generation. Maybe some things in my experiences could be useful to them. And so I begin to think back, where is the first example of an engineering accomplishment that did not involve Legos or Lincoln Logs? And that took me back to 3rd grade science fair. And I grew up in a small town in Texas outside of Houston, Sugar Land, so this is 1977. And in this science fair, I built something that I called a magic box. It's basically a wooden box. You kind of look through a hole here. And with a combination of a partially silvered mirror and a variety of lights that you could switch on and off, you could create a simple optical illusion. And I think this is my first memory of doing something inventive and creative, and it sort of captured my interest. I like the optics part of it and the materials part. But I have to say that I probably wouldn't have done any of this if it weren't for the encouragement of my parents. And I think at this age, parent involvement is absolutely critical. So I'm really happy that my parents are here today, and I owe everything to them, sort of encouragement and getting me started on this path. So they had full responsibility and full credit for getting me involved in this science fair. So the other thing you might notice here, if you kind of look at this and you look at this, my parents also had responsibility back in those days, my mom in particular, for home haircuts. As you might notice, this is a very interesting hairstyle that I'm sporting here. There's a peculiar feature right there that I have no idea. I have no explanation for that at all. But this was, you know, small town Texas, disco days of 1977, so this is the way it was, you know, and you can kind of get by in those days. So, you know, this was the first of a number of different science fairs, a number of different interesting hairstyles. I won't step you through all of those things, but really kind of fast forward 20 years later. And what happened is I got bigger, my hair got shorter, these days cut by professionals who are actually trained in the art. And I suspect my dad wishes he could say the same thing. But the other thing that happened here is that the optics boxes got way more sophisticated, you know. And well, I sort of decided in these early days, you know, you want to do innovation and engineering, you really need to establish a firm foundation in the fundamentals. So I went off to undergraduate school at University of Texas at Austin, majored in chemistry and physics. Really was a very focused student, did well. And decided, you know, upon graduation that maybe I should, you know, see if I could run with the big boys. And so I decided to apply to the biggest, baddest place I knew of at that time, which was MIT. And I got accepted, was thrilled with that. And so I came to MIT as a graduate student and hooked up with this guy, Keith Nelson, and spent 6 years building this monstrosity. What we were doing back in those days with Keith is trying to develop techniques for using lasers, very short pulse lasers, for characterizing materials in ways that didn't require any physical contact. And in particular, we were looking at materials in very thin film form. And materials in that form are very fragile. You can't contact them typically without destroying them. And so what we were doing with Keith is developing picosecond lasers. These are huge lasers. It's about 1 meter scale, just to set the scale here with a big cooling water station over here to allow it to operate. The laser would come out and we'd actually shine it on the sample in a way that would initiate an acoustic vibration, very high frequency acoustic mode in the film, and you can monitor that in real time. And from the data that you collect in that way, you could use software analysis algorithms that we developed to extract intrinsic mechanical properties, how stiff the film was, how strongly it was bonded to the substrate, how effective heat was flowing through it. And we wrote a number of scientific papers on those technologies and that type of approach. And we found that there were a number of industry groups who were interested in that. So kind of on the side, in parallel with the research program, we would do analysis of car paint, you know, on bumper parts that Ford would ship over to us. We did analysis of hard coatings on razor blades from Gillette. We also did some analysis of thin metal films from Intel on silicon wafers. And so that was kind of amusing. I think it probably would have stopped at that point, you know, in ordinary times. But this was early 90s at MIT, and it was anything but ordinary times. There was an incredible enthusiasm back in those days in entrepreneurship and startups. And the Lemelson Foundation was just coming up to speed in those days. And so that was in people's consciousness. And as a result, you know, they also had this business plan competition. So we decided, hey, you know, we have these techniques. Various industry folks are interested in it. Why don't we explore the business opportunities? So we went down the street, teamed up with some folks from Sloan School, put together a business plan as part of this competition, did a lot of industry surveys to determine, you know, what are the different modes of application of this technology. And we did pretty well. It turned out that there was a pretty interesting business proposition. Forget about the fact that the laser apparatus is this monstrosity spread out over the whole room. If you could, you know, and this was just pure fantasy, if you could put it at that time, if you could put it in a box like that, maybe other people could use it. And you know, we made it all the way to the final 5. Now this is incredible competition. Everybody on MIT campus was involved in this or watching it, and so the competition level is extremely high. We did not win, but I told the guys at the time, this isn't the end of the game. The game is to actually do it for real. Go off and start a company and sell tools. And that's in fact what we did, because out of this competition, we now had a business plan. We had a series of contacts in the venture community, those who were involved in judging this kind of competition. And so we went off and launched a company. And to make a long story short, we took that whole room scale set of optics and lasers and so on, and figured out ways to miniaturize everything. We actually ended up building our own laser. It's about the size of a thumb. We had custom digital optics here, another CW laser fast detector over here. So all the optics were housed in this head. The laser beams would come down here. You put your sample here. This would record the information and in an automated way provide some of this key mechanical property evaluation. So we made tools like this, and it turned out the killer application was actually evaluation of thicknesses of thin metal films that are used in computer chips. Determining that in other ways is essentially impossible. You can't contact the sample, and you can't see through it. So you have to use some kind of unusual approach like this. And we developed this technology to the point that it provided angstrom level, atomic level precision in the measurement of these thin metal films, which was just incredible at that time in terms of measurement capability. And because the measurement could be done in very short periods of time, just 1 second shot on the sample, by moving the sample around, you could develop maps, thickness maps. And so it would inform a semiconductor manufacturer of variations in the thickness of the thin metal films, and that could be used to feedback on the manufacturing process in a way to improve the yields. And so you could do this mapping over a full wafer. This full scale here is only about 300 atoms. You could do fine mapping in this way. Total variation in thickness there is about 50 atoms, all in a completely non-destructive, non-contact way. And so it turns out that capability was in interest to lots of folks. So we started selling tools. That worked out well. This was a particularly memorable event. So this was the Active Impulse team. Tight-knit, small, lean, mean team. We're actually sitting in the back of an 18-wheeler, and behind us is a crate that contains our very first commercial tool. It's like $250,000 tool. I mean, these sort of lumpy type of sales. And we were getting ready to ship this from Massachusetts to California. And it was really a transformative event for me, because it was at this moment that I realized this is what I want to do research and translate it into products and ship them to customers who could use them to advantage. So this is John Hanselman. A lot of the guys here are in the room right now. There's Keith. There's Jonathan Fleming was a key investor in those days. Jim Zabrania was an intern. Martin Fuchs, the lead engineer, and Matt Benet, another guy involved in this team. So that was fantastic. It was fun. It was clear that I wanted to do this. And it was fun because you were working with talented people. And these bonds last a long time, it turns out. Here's, we reformed the band, so to say. And this was actually last night. And it turns out that everybody had their AIS t-shirts from those days. It was amazing. This is 15 years later, right? And that's everybody. And Sarah Leggett is actually in the audience. She was another angel investor for that company. And this is great. It doesn't get any better than that. It really doesn't. And so this is what we decided we wanted to do. It eventually got acquired by Philips, and it's still sold in a worldwide scale. Very sophisticated tools now, $1 million embodiment right there. So a lot of additional bells and whistles. The key measurement metrology is the same. So that's what we're doing. When I finished up my graduate work, I decided, this is great, but it would be better, instead of measuring somebody else's samples, to make your own. Get involved in the materials and the device side of things. And so I went to Keith, and I asked him, this is kind of what I want to do. I want to get into materials and devices. I want to work with somebody who's doing innovative research in that area for my postdoctoral experience. And almost within 1 second, he said, oh, you need to go work with George Whitesides. He's doing stuff like this. And my response was, who's George Whitesides? I was very focused on my own work in those days. He was a very famous guy. I had no idea. But I trusted Keith, so I went down the street, met with George, went to a few group meetings, and joined up because he was doing some really cool stuff. And in those days, we were developing printing techniques that would allow us to pattern electrode structures and other things as alternatives to the ways that operation is done in the conventional manufacturing process. And one of the things that we could do that was kind of unique was that we could print electrode structures on fine threads of glass, optical fibers in particular, and these form the backbone of optical communication systems that are used for internet and phone lines these days. And, George didn't know much about optical fibers. I didn't know much either. But, we had this crazy idea that, if you could form electrode structures on a fiber like that, what if you could put a circuit on an optical fiber and design it in such a way that you could apply a voltage or flow a current and manipulate the way that light is transmitting down that fiber? And that was sort of a wild, crazy idea, but we didn't know enough to assess whether it was realistic or not. And so, after spending some time in George's group and doing this sort of stuff, I decided I want to put myself in a lab that would optimize the chances for doing this translation from research to products. And I liked optics, and fiber optics was interesting. Back in those days, I think, in my view, Bell Labs was the premier place for physics and material science. And so that's why I went there, because it was embedded in an engineering company that built products. And so I went off to Bell Labs, and carrying with me this idea, and so we got involved in fiber optics, did a variety of things. But what was sort of a highlight from my time at Bell Labs is we were able to push that idea, that crazy idea hatched in the labs at Harvard, we didn't know anything about fiber optics, into the most sophisticated communication system that Lucent was selling at that time, a 40 gigabit WDM telecommunication system. And this is one of the devices. They use these internally for their own networks. They sold them externally. It's basically one of these fibers with this kind of microelectrode structure on its surface. So it was used at the back end of a network. So the signal would come in if somewhat degraded. This device was designed to clean up that signal to enable fewer errors in the propagation. And this product came out of the efforts of a small team, very much analogous to the one that worked so well for us back at Active Impulse Systems. And this is the team, sort of analogous to that AIS photo. This is a picture of us building these boxes sort of in our labs, and they were launched off into the first customer trials of these 40 gigabit systems at Global Crossing. At that time. And so that was just a really fabulous time back at Bell. And what was amazing was a tiny little team of guys. If you look at the press release associated with the announcement of this Lambda Extreme network system, they noted that 3 magical ideas from Bell Labs allowed it to happen. This is one of them. And so it's sort of remarkable that Lucent was 100,000 employees in those days. Multi-billion-dollar company. Is just a ragtag, tiny little team like this was making a contribution. And so that was fun. I think I would have stayed at Bell Labs forever. It was a good place for me. I really enjoyed it. But you might notice in this press release, there happens to be a stock ticker right there. And that stock price was about a factor of 20 from its peak at that time. And it ended up dropping another factor of 20. And things get uncomfortable in a lab that's attached to an unhealthy company. So partly for that reason, partly because I wanted to get back into mentorship and interacting with students, I decided to go back to university. And what we did is set up a research program that looked at the possibility of printing not only microelectrode structures, but actually active materials. So you could do not only electrodes, but transistors, LEDs, things like that. And it took us a while to figure out how to do that, but we eventually did, and it involved a process that was referred to in the video. It's taking a semiconductor wafer, exploding it into a lot of tiny pieces, and use these printing techniques to reorganize them and print them down onto target substrates of interest. Turned out that struck us as a very powerful capability, formed the foundation of a company that we launched called Simprius, who decided that the killer application for that kind of approach was in an unusual photovoltaic system that instead of using big solar cells, used very tiny ones. It's going exactly sort of in the opposite direction of what you might ordinarily think of as a design strategy for PV. So make very tiny cells, in this case, each one about the size of a grain of sand, and then we print them out in a low aerial coverage on a glass wafer. You slap on top of that focusing lenses, and you can make very efficient utilization of extremely high efficiency PV material. And you can do conversion at module level efficiencies that are sort of world record levels at a cost competitive point. So that idea emerged last year in the form of a commercial product, the first one of which was sold to the public utility Tucson Electric Power. This has been operating in the desert for almost a year, generating several megawatts of power by now. And Simprius is off into another stage of its development, because today Siemens announced the acquisition of an equity stake in Simprius, and they will provide global partnership for wide-scale deployment of this technology. And so this is the Simprius team. Several of the Simprius guys are in the audience, and it's been a real pleasure to be able to interact with them and take some of these ideas up a few levels and make them into a technology that can have broad societal significance. So that's PV. What we also found is that you could print these active materials not only on plates of glass, but almost anything. And if, in fact, we could print these elements on rubber balloons. And it turns out that if you can do that, you can make some pretty interesting surgical devices. So a completely different field of application, same core idea. You could begin to think about systems that could have positive impact on human health. And this is an example of one of these, what we're calling instrumented balloon catheters that are used in the treatment of cardiac arrhythmias. And this is being pursued at a commercial level by the company MC10, which is a local company here, in close collaborations with cardiologists who do these kind of procedures routinely with conventional technologies to provide us with insights into the application requirements. And so this is a small team that exists now at MC10. You'll notice that I'm not in this picture anymore because I kind of have a different role now on these things. I'm not the guy in the trenches, but trying to see these efforts and sort of motivate people and provide some guidance and mentorship. So these are extremely talented folks, and we're moving that forward as a product. So that's kind of my path, what kind of technologies I've been involved in. If you look at the development timeline, back in Sugar Land, we had the Magic Box. It was 20 years before we did anything realistic. I think it's 3 years from the point where we knew we could build these boxes to the day that we were selling them. Moved to Bell Labs, similar time frame associated with the fiber devices. There was a gap here because we had to figure out how to print semiconductors. So once we did that, we were able to launch into PV and also biomedical devices. I didn't say much about it, but MC10 has a joint development effort with Reebok that is anticipated to yield a product in early 2012. So this is a sort of a funny collection of stuff if you think about it. The common thread here is that it's materials for optical or electronic systems. That's the common connection. So the key thing is that you develop a core expertise and then work with others to leverage it into various areas of application. That's been a working, effective model for us over this time period. So I have no idea where this goes into the future, but I'm definitely looking forward to more stuff of this type. So what do you learn from this? Well, lots of stuff. I tried to condense it down into 3 items. The first one is that I would recommend, you're interested in innovation, pursue big problems. The small problems will work themselves out. People in this audience should be focused on big problems with significant societal implications. And as you work on those big problems, try to think of simple ideas and simple concepts. Those are the ones that end up working, provided that you're persistent with those concepts and you're focused on the goals. So some of the ideas that you have won't work. In fact, most of them won't. But if you're focused on the goals and flexible on the ideas, I think it's a working approach. The other thing that's been effective for us is teamwork, working with talented colleagues and learning from them to get yourself into areas that would be otherwise impossible. And the last one is get lucky and capitalize on those opportunities. And by that I mean, I don't believe in luck, but create your own luck. And that has to do with being in the right place at the right time. And for me, the right sorts of places were labs at MIT or Bell Labs or Harvard or University of Illinois. And you never know when the right time is, so try to be there all the time and watch for the right moment. And take advantage of it. Be observant, realize when that moment has happened, and then move quickly to capitalize. Okay. The other thing where I have gotten lucky, I think, is working with excellent people. And I think if you're going to do commercialization, you have to work not only with scientists, but business people as well if you want to be effective. And so we've been very fortunate with very talented CEOs, starting with John Hanselman back in the AIS days, but moving to Joe Carr and Dave Icky these days, and you need capital to do things. So it means you need to interact with venture capitalists, and some of these guys are good, some better than others. I think these are sort of best in the breed. Clint Bybee and Carmichael Roberts, they invested with us almost by definition, then they're good. But they invested, you know, in the early days. That's when it's hardest to invest, when it's not clear, you know, how things are going to work out. But they've been critical, and you know, neither of these companies are at endpoint yet, but I think they're headed in the right direction. So I think things will work out for these guys. But probably even more importantly are the scientific mentors and advisors that I've had over the years. I'm nothing without these guys. And I've mentioned Keith Nelson and George Whitesides already. There's a collection of folks back at Bell Labs who are really, you know, had a huge impact on the way that I think about science and innovation and how to do things. Pierre Wiltzius, the guy who hired me, Federico Capasso is in the audience, was a boss of mine for a while. Cherry Murray as well. Mark Cardillo's in the audience. He was a close confidant during those years. And Adi Adesat also, Dean of Engineering at University of Illinois, close collaborator and advisor. So these guys are critically important. The other important person that I would be remiss in not mentioning is my wife. I think she's much smarter than I am, much more insightful than I am, and she provides fantastic advice to me as well. So, you know, in terms of these guys, you know, I've asked them many times, you know, how do I repay you for all of this advice and mentorship that you've given me over the years? And to a person, they tell me, provide the same kind of advice to the next generation. That's the way you repay our contributions to you. And so that's what I do these days, and that's where my real focus is providing mentorship, mostly to folks in my group. So I run a very large operation here. We have 30 undergraduates doing research for course credit just this summer, and 40 graduate students and postdocs. And my approach is really to lead by example and to work with these guys rather than manage down on top of them. And so if you notice, that's me right there, sort of embedded in the group. So the other aspect of an operation like this is these guys are hungry, and it's my job to keep them fed. So Mike Sema mentioned Lamborghinis and stuff like that. I think this prize money will be better spent in supporting these guys and helping to pay their salaries. So with that, it brings me full circle then in terms of mentorship, because I think that's a key mission of the Lemelson MIT Foundation. And I just can't imagine anything more important. And so I'd like to thank Dorothy Lemelson and the Lemelson family again for this wonderful foundation and the legacy that it's establishing over the years. So thank you very much for your attention.